Okay, so this exercise or video is going to show you several counting examples where you have permutation, combinations, and I even throw in some multiplication principle and some addition principle problems. So let's look at some of these. Number one says, suppose we have to select 5 managers from a list of 10. How many ways can this be done? Well, first of all, repetition wouldn't make sense because you wouldn't choose the same manager twice if you choose 5 managers. And then secondly, if you choose 5 managers, if all you have to do is choose 5 managers and you want to know how many ways you can choose 5 managers, all you're really wanting to know is how many 5-element subsets are possible, because the order does not matter. So order is irrelevant here, and since order is irrelevant, we're looking for how many combinations we can get, so that would be 10C5. Now on each of these, I'll leave you to go to the calculator to calculate the particular calculation that you need to calculate. For instance, here you can go to the calculator and do 10C5 and get 252. Now here, suppose we're going to select a manager. In other words, we're going to assign a manager, an assistant manager, and a night manager to 3 of these 10 people. How many ways can this be done? Well, again, we're not going to assign manager to an assistant manager and night manager to the same person, so repetition wouldn't make sense. And if we chose them in this order, A, B, and C, then A would be the manager, B would be assistant manager, C would be night manager. But notice we can also assign them different ways. If we could also let C be manager, A be assistant manager, B be night manager. So that would be something new. So that means that the order is relevant here. So that would be a permutation problem for 10P3. The next one says, how many ways can a 3-card hand be selected from a standard 52-card deck? In other words, how many 3-card hands are possible? Well, repetition wouldn't make sense because you're not going to get, say for instance, the 3 of clubs. You're not going to get that card twice, so repetition wouldn't make sense. So let's say you get the 3 of clubs, the 9 of diamonds, and the 8 of spades. Well, if you rearrange those 3 cards, it's still the same 3-card hand, even if they're in a different order. So order is irrelevant in this case, so it would be a combination problem. So you would do 52C3 and calculate that on your calculator. Now, if you were to select 3 cards and assign the cards to 3 different players, then that would force the order to matter. Because now, if you drew the 3 of clubs, 9 of diamonds, and 8 of spades, then that might imply that that player A gets the 3 of clubs, player B gets the 9 of diamonds, and player C gets the 8 of spades. But if you drew them in a different order, then player A might get the 3 of clubs, player B might get the 8 of spades, and player C gets the 9 of diamonds. So by assigning them positions, that makes the order relevant. So this example would be a permutation problem. Now, in this example, number 5, if a card is selected from a standard deck and then we put it back and reshuffle it and then draw again, so let's say we do this 3 times, how many 3-card hands can you receive? Well, now, since we're putting the card back, repetition is possible. Now, once repetition is possible, permutations and combinations go out the window, and you have to revert back to the multiplication principle. So here we say how many cards are possible for the first selection. That'd be 52. How many cards are possible for the second selection? Well, since we put the card back, it's still 52. And for the third selection, we put the card back again, so it's still 52. So it would be 52 times 52 times 52, which is 140,608. So that's a multiplication principle problem. Now, number 6 says, at a Fiat dealership, a total of 3 cars of a particular model must be transported to another dealership. If we have 25 cars of this type on the lot, how many choices are available for transport? Well, repetition doesn't make sense, and the order in which they're selected is irrelevant. If we choose car 1, car 15, and car 20, it doesn't matter what order we choose them, it's still the same 3 cars. So this would be a combination problem, 25C3. Number 7 says, what if we basically did the same problem, but instead of asking how many groups of cars we can select, what if I said, how many ways can they be loaded onto the truck? Well, now, if you select them in this order, car 1, car 15, and car 20 would be loaded on in that order, but if you take the same 3 cars in a different order, then that would give you, as I said, a different order in which they're loaded onto the truck. So basically the way the question asks here on number 7 forces this to be a permutation problem because the order is relevant here. We want to know how many arrangements are possible, so that would be 25P3. Here I said, what if we have 25 cars of a certain model, and let's say 15 have automatic transmission, 12 have leather seats, and 10 cars have both. Now, this might sound like some of the problems we ran into when we were doing those Venn diagrams and the addition principle, because that's exactly what this is. The question says, how many have either automatic transmission or leather seats? Well, that's looking for the union. So if A would be the automatic transmission and B was leather seats, then we're looking for how many's in the union of A and B. So you might remember, to find out the number in a union, you take the number that's in the first set plus the number that's in the second set minus the number in the intersection. Well, there's 15 in the first set, there's 12 in the second set, and there's 10 in the intersection. So calculating that, I get 17. The second question says, how many have neither automatic transmission nor leather seats? Well, if 17 have either one or the other, then we can simply subtract 17 from the total cars, 25 cars, and that means that those 8 that are left, they must have neither automatic transmission nor leather seats. You can draw a Venn diagram for that one if you need to. Social Security numbers consist of 9 digits, 0 to 9. Now remember, when you go 0 to 9, that's actually 10 digits. I'm sorry, I said 9 digits, but, well, it is 9 digits. Social Security card has 9 digits, but it's, let's see, 431, yeah, it's 9 digits. But it's out of 10 digits. I'm sorry, it's out of 10 digits. 0 to 9 is 10 digits. So, if there are no restrictions, how many Social Security numbers are possible? Well, let's say we were going to write down just a random Social Security number. Well, there would be 10 ways to fill out the first spot. There'd be 10 ways to fill out the second spot, 10 ways to fill out the third spot, and so on. So we would have 10 ways to fill out each of the 9 spots because we're allowed repetition here. There's no restrictions. So that would be 10 times 10 times 10, 9 times, which would give me 10 to the 9th, or 1 billion. Now, a billion is probably enough, but anyway, you probably aren't going to have a billion because, you know, I doubt someone's going to have this Social Security number. So there's probably some Social Security numbers that have to be excluded. But anyway, the maximum you could have under that system would be a billion. Let's talk about license plates. Suppose we have license plates in one state have 4 letters followed by 2 digits. How many license plates can be created if there are no restrictions? Now, repetition is allowed here. So it says, so we actually have 2 operations here. One operation is to figure out how many ways we can select the letters, and the other operation is how many ways we can select the digits. Now, how many ways can we select the letters? Well, repetition is allowed on the letters, so there's 26 ways to choose the first letter, 26 ways to choose the second letter, 26 ways to choose the third letter, 26 ways to choose the fourth letter. So there's 26 to the 4th power ways to choose the letters. And there's 2 digits, so there's 10 ways to choose the first digit. There's 10 ways to choose the second digit, so that gives us 100 ways to choose the digits. Now, to find out how many ways you can do these operations one after another, you have to multiply these 2 numbers together. So multiplying them together gives me 45,697,600 license plates possible. Now, if I say only the letters cannot be repeated, so that means we can repeat the digits, then if the letters cannot be repeated, then when I do the letters, I have to, where am I at here? Here we go. I have to consider, since the letters can't be repeated, I would have only 26 times 25 times 24 times 23 possibilities for the letters, which is 358,800. And then the numbers can be repeated, so I'd still have 100 for that, and then I multiply those two numbers together to get the total number of license plates. But then let's do one more thing. What if only the digits cannot be repeated? So now the letters are repeated, but the digits aren't. So for the letters, I go back to that, what I got up there at the top, 4, 4, 5, 6, 9, 7, 6. And now for the digits, I can't have repetition. So there's 10 ways for the first digit and 9 ways for the second digit. So that gives me 90. And then I have to multiply these two together to get the total. Okay, 41,127,840. Look at number 11. We get 20 disk drives. 4 are defective, and we're selecting a sample of 2. How many samples can be selected? Well, the order doesn't matter, so that would just be out of the 20 drives, how many subsets of 2 are possible? So that'd be 20C2. Second one says how many of the samples contain 2 defective drives? Well, remember, this 2 defective drives can only be selected from the defective drives, and there's 4 defective drives. So you have to say, you have to narrow the population from 20 down to 4 this time, so it's 4 choose 2, which is 6. And then if we were assigning each drive to a different position, like we're assigning one to be tested and one to be sold, that would force part A to be a permutation problem, because now the order matters, because we're assigning the drives to positions. So that would be 20P2. Now, suppose we take a 5-card hand and we want to know how many ways we can get 3 kings and 2 aces. Well, this is 2 operations. You got to figure out how many ways to get 3 kings and how many ways to get 2 aces and multiply them. Well, out of 4 kings, choose 3. That's how many ways you can choose 3 kings. And out of 4 aces, choose 2. That's how many ways you can choose 2 aces out of 4. So multiply these two together, and you get 4 times 6, which is 24. So there's 24 ways. How many ways can you get exactly 3 4s? Well, out of the 4 4s, you do 4 choose 3, and that tells you there's 4 ways to get 3 4s. But with those 3 4s, you got to have 2 cards that are not 4s. So there's 48 cards that are not 4s. So you have to figure out how many ways can I choose 2 cards that are not 4s. So that's 1128. Well, then you have to multiply these two together, because it's 2 operations, getting the 3 4s and then getting the 2 cards that are not 4s. So to do those in tandem, you have to multiply them, and you get 4,512 ways. The last one here, this one says at least 4 hearts. Well, when you do 4 hearts, at least 4 hearts in a 5-card hand, you got to figure out how many hands have exactly 4 hearts and how many hands have exactly 5 hearts, and add them together. And that's what's tricky here. So you have 27,885, because you do 13 hearts choose 4 and 39 non-hearts choose 1, and multiply those together. And then for 5 hearts, you just do 13 hearts choose 5. You can write 39 choose 0, but you don't have to, since that's 1. And then you add those two together. And so the total number of hands that have at least 4 hearts would be 29,172. There's a couple of other questions here that I'll leave these for you to read, and you can freeze the video if you need to, and you can see how they're worked. And there's also some other problems on my lecture notes for this topic. If you get a hold of my lecture notes, you can go down there and see some other practice examples that you could practice on. So that pretty much completes the counting lectures, and I guess have a good day.